Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Sciences, SOS, Bachelor of Science, Multidisciplinary, BSCM, Botany, BBYCT 133 Plant Ecology and Taxonomy, Block-1 Ecology and Ecological Factors, Unit-2 Ecological Factors, Soil and Water. 2.1 Introduction. In the previous unit, an introduction regarding the various abiotic factors that occur in environment has been given. Abiotic factors form an important component of an ecosystem and affect the survival of an individual, population, or community to a greater extent. The present unit provides you detailed information about the two major abiotic factors, i.e., soil and water. Expected learning outcomes. After the study of this unit, you should be able to describe the process of soil formation, describe the composition of soil, enlist the properties of soil, describe the structure of soil horizon, enumerate different forms of water and their sources, enlist the properties of water, and discuss the importance of hydrological cycle. 2.2 Soil. Soil forms the outer layer of the Earth's crust. The word soil is derived from the word solemn, meaning earthy material that supports plant growth. Soil acts as a substrate that provides mechanical support to plants and as a reservoir of water and nutrients for plants. It is composed of inorganic and organic materials. Inorganic components include mineral elements derived from parent rock material. Organic matter comprises of organic wastes, dead remains of plants, animals and their decomposition products. Large number of algae and microorganisms such as bacteria, viruses and fungi form an important component of soil. 2.2.1 What is soil? Soil is a natural resource formed by weathering, breakdown of rocks. It has been defined as the matrix, sand-silt clay, containing living biomass and dead organic matter with some concentration of air and water. It is a rich source of organic and inorganic materials that support plant life and microscopic communities. Inorganic material includes mineral elements derived from weathering and fragmentation of parent rock material. Organic components include organic wastes, dead remains of plants and animals and their decomposition products. 2.2.2 Origin and formation of soil. Various models have been proposed to explain the formation of soil. The process of soil formation, soil genesis, was proposed by Hans Jenny, 1941, and Roy W. Simonson, 1959. According to these authors, soil formation consists of, includes delete, two steps, 1. Accumulation of parent material, and 2. Differentiation into different horizons. Organic matter is added to soils after decay and decomposition of remains of plant and animal. The rate of soil formation is regulated by environmental factors. Soil formation. The process of soil formation begins with the changes in the parent material. Rocks, accumulation of raw material followed by buildup of organic materials at the surface. Various physical, chemical, biological, and anthropogenic processes are involved in the alteration of the parent material to form soil. Two main steps involved in soil formation include 1. Weathering of rocks. The breakdown of rocks is called weathering. It can be physical or chemical. Physical weathering occurs by mechanical forces. Changes in temperature cause contraction or expansion of rocks, leading to formation of cracks and fissures in rocks. This breaks rocks into smaller pieces. Low temperatures freeze the water present in the rock crevices, causing expansion, and this force breaks the rocks into small pieces. Besides these, hail, rainfall, wind also help in breaking off rocks into smaller particles due to friction. Chemical weathering is brought about by action of water or activities of organisms present in soil. Water brings chemical changes in rocks due to dissolution, oxidation reduction reactions, and organic acids produced by microbes assist in the breakdown of rocks and add organic matter to soil. To mineralization and humification, the small pieces of rocks or particles produced by weathering of rocks get converted into a homogeneous matrix via the process of mineralization. Plants and animals play an important role in this process. The roots of the plants invade the soil particles, further breaking the particles into fine material. The microbes associated with the roots of plants secrete organic acids and humic acids that further assist in breakdown of rock material to fine soil particles. Microorganisms such as bacteria, fungi, and actinomycetes assist in the decomposition process. In the process, organic compounds get converted into inorganic nutrients. The breakdown of organic compounds leads to formation of simple products such as carbon dioxide, water, and minerals. The process is called mineralization. Incompletely decomposed organic material left after mineralization forms the humus, which is a dark, homogeneous, amorphous, colloidal substance. Humus gives loose texture to the soil, which provides aeration and helps in retaining water and nutrients. The process of soil formation depends upon several factors such as the parent material, rock, climate, topography, relief. Fig 2.1. Factors affecting soil formation include: the development of soil profile is influenced by several factors. These mainly include changes in the parent material, climate change, topography, organisms. All these factors change the characteristics of soil and give it a distinctive profile. Parent material. The parent material plays an important role in deciding the characteristic of the soil. The chemical composition of the parent material determines the properties of the soil. Color, texture, structure, mineral composition, and permeability of soil depend upon the parent material. A soil developed from coarse-grained parent material is resistant to weathering and is coarse in texture. The soil formed from limestone possesses high level of soluble bases and is fertile in nature. The soil formed from the parent material, which is low in soluble ions, is acidic. This is because water moving through the soil removes the bases and substitutes them with hydrogen ions. Soils developed from sandstone are low in soluble bases. Climate. A climate influences soil development and soil chemistry. Climatic factors regulate the rate of chemical reactions occurring during soil formation. Precipitation also affects development of horizons as the translocation of dissolved ions through the soil gets affected. Soils of hot, dry desert regions are generally devoid of organic material because less vegetation and few microbial species are available for decomposition. The lack of precipitation inhibits chemical weathering, leading to coarse textured soil in arid regions. In contrast, high rate of annual precipitation flushes out organic material from the Soil. The cold temperatures restrict the microbial activity, hence affecting the buildup of organic matter in the tundra region. In the warm and wet tropics, rapid rate of bacterial activity promotes decomposition leading to buildup of high organic matter. The rate of biological processes gets enhanced in presence of rising temperature. The rate of reaction gets doubled for each 10 degrees Celsius rise in temperature. Enzyme-catalyzed reactions are sensitive to high temperatures and attain a maximum between 30 and 35 degrees Celsius. The velocity of water determines the rate of soil erosion and deposition of organic material. The rate of percolation of water, i.e., the movement of water from one part of the soil to another, is also affected by climate. The rate of absorption of the solar radiation is regulated by soil properties such as color. Dark soils absorb more radiation. Topography, elevation, it is a factor that poses a significant impact on soil formation because it determines runoff of water. Slope angle and length affects runoff generated when rain falls to the surface. Water erosion is more effective on steeper, unvegetated slopes. Water moving across the surface drives away the parent material, thus impeding soil development. The amount of water and its rate of flow increases down the slope direction. Biological factors. The biological components of the soil include vegetation, microorganisms, and associated fauna. These organisms influence the soil composition to a greater extent. Soil-forming fauna mainly includes microorganisms such as bacteria, fungi, actinomycetes, earthworms, small arthropods and burrowing animals, rabbits, moles. Biological processes carried out by organisms present in the soil or associated with roots of the plants help in build of organic matter in soil. Pioneer species such as grasses and algae lead to build up organic matter on the surface of the parent material. The soils that possess less number of microbes, desert soils, are also not well formed and lack organic matter. Timed all pedogenic, soil-forming processes occur over time. Young soils show only minimal profile development, i.e., poses only horizon A, while the mature soils poses all the horizons. 2.2.3 Composition of soil. Soils are mainly composed of four elements, namely minerals, organic matter, air and water. Most of the top soils contain about 45% minerals, 25% water, 25% air, and 5% organic matter. These percentages can vary tremendously depending upon the type of soil. Minerals, they are of dissolved substances. These mainly include elements such as carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, various alkaline earth metals. Soil organic matter. Microbes and fungi or their parts, as well as waste products in various stages of decomposition. Organic compounds. The elemental composition of soil includes carbon, oxygen, hydrogen, nitrogen, phosphorus, and sulfur. Minor portion of the soil but has a very strong impact on the pH. Function of soil. Water. It also helps in binding water to the soil and holding the soil aggregates together. Organic matter has high cation exchange capacity, CEC. Negative charge on the organic matter of soil attracts the cations necessary for plant growth and reproduction. The soil having organic matter content of 20 to 35% on a dry weight basis is considered as organic soil. Air and water. Particles. The amount of air present in the soil depends upon the amount of water. If more water is present than pore space can hold, it is said to be saturated. If soil is saturated by water, little air is available. In anaerobic conditions, air spaces are filled with water, oxygen and other gases are unable to diffuse from the outside atmosphere and converts organic material into useful elements. In soil depends up ecology and ecological factors. Composition of soil. They are formed by breaking of parent rock material and addition of dissolved substances. These mainly include elements such as carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, aluminium, silica and various alkaline earth metals. Soil organic matter, SOM. Organic matter consists of dead plants, animal, microbes and fungi or their parts, as well as waste products in various stages of decomposition. It is formed as a result of decay and decomposition of organic compounds. The elemental composition of SOM includes carbon, oxygen, hydrogen, nitrogen, phosphorus, and sulfur. Organic matter forms a minor portion of the soil but has a very strong impact on the P function of soil. Organic matter is able to absorb and hold large quantities of. It also helps in binding water to the soil and holding the soil aggregates. Organic matter has high cation exchange capacity, CEC. Charge on the organic matter of soil attracts the cations necessary for plant growth and reproduction. The soil having organic matter content of 20–35% on a dry weight basis is considered as organic soil. Air and water occupy pore spaces between the solid soil. Particles. The amount of air present in the soil depends upon the amount of water. If more water is present than pore space can hold, it is said to be saturated. If soil is saturated by water, little air is available. In anaerobic conditions, air spaces are filled with water, oxygen and other gases are unable to diffuse from the outside atmosphere. Air helps in the process of oxidation and converts organic material into useful elements. The amount of water held in soil depends upon its texture and structure. In sandy soils, water drains quickly, while in clay water is held between the soil particles. In areas of low evaporation rate, water moves downward and dissolves the soluble minerals together with soluble humus material, and the process is called leaching or alluviation. Water present in the soil is of different types. Gravitational groundwater, the water that moves into the soil under the influence of gravity after rain or irrigation, is the gravitational water. Capillary water, the amount of water retained in the soil against the pull of gravity. The water is enclosed in between the spaces between soil particles as thin film. This is the most important source of water utilized by plants from the soil. Hygroscopic water, the amount of water in air-dried soil. The water is present in relatively small amount. The moisture-holding capacity of the soil is governed by its properties such as particle size, porosity and texture. Maximum amount of moisture the soil can hold is called maximum retentive capacity. In this condition, air present in the soil pores gets replaced by water after heavy rainfall or irrigation. If water supply is stopped, water form larger pores, macropores, drains out and pores gets filled with air. while water remains retained in smaller pores, micropores. The water left in soil after draining out of gravitational water is called field capacity. It is defined as soil with water content of minus 0.33 bar suction pressure, 0.0033 MPa. It is generally expressed as the percentage of the weight or volume of soil occupied by water when saturated at a standard temperature. It varies with soil texture, i.e., proportion of sand, silt and clay. At certain point, moisture decreases to a level that is not available for plants. Soil is supposed to have reached a wilting point. It is defined as the amount of water at minus 15 bar suction pressure or minus 1.5 MPa. Structure of soil. It refers to the arrangement or grouping of soil particles. This can occur as a continuum, single granule, large, or many aggregates, small. Soil particles are of different sizes. Gravel consists of small, loose, rock particles larger than 2 mm. These are the largest particles in the soil. Then there are sand particles. Are the largest, delete, ranging in size from 0.05 to 2.00 millimeters. There are also silt, consists of, delete, particles ranging from 0.00 to 0.05 millimeters, and clay contains particles less than 0.002 millimeters. Sand and silt are the inactive or inert part of the soil matrix. They do not retain soil water or nutrients. Clay is the active portion of the soil matrix. Large amount of surface area per unit mass of clay and surface charge attracts ions and water. The negatively charged clay particles attract positive ions cations and release them to the soil water. Cations such as potassium, K+, calcium, Ca2+, magnesium, Mg2+, iron, Fe2+, and Fe3+, and zinc, Zn2+, are essential plant nutrients held by the soil particles. They play an important role in plant growth and development. This property of soil is based on the soil particles. Percentage of sand, silt and clay. Soil texture varies according to of these three, Table 1. The proportion of sand, silt to 100% for all mineral soils. Percentages. T and clay always adds up. Texture depends upon the parent material. A strongly developed structure possesses heavy texture. Depending upon the percentage of sand, silt and clay, soil texture H. This property of soil is based on the soil particles. A soil texture includes the percentage of sand, silt and clay. Soil texture varies according to of these three, Table 1. The proportion of sand, silt, and clay always adds up to 100% for all mineral soils. Texture depends upon the parent material and soil forming process. A strongly developed structure possesses heavy texture. Depending upon the percentage of sand, silt and clay, soil texture H. Been divided into different classes organized into a textural triangle. A soil containing 15% clay, 20% silt and 65% sand is sandy loam, and a soil containing equal amounts of sand, silt and clay is clay loam, Fig 2.3. Till now, 12 soil textures have been and soil forming process. Texture depending upon the percentage of sand, silt and clay, soil texture H. Been divided into different classes organized into a textural triangle. A soil containing 15% clay, 20% silt and 65% sand is sandy loam and a soil containing equal amounts of sand, silt and clay is clay loam, Fig 2.3. Till now, 12 soil textures have been divided into different classes organized into a textural triangle. A soil containing 15% clay, 20% silt and 65% sand is sandy loam and a soil containing equal amounts of sand, silt and clay is clay loam, Fig 2.3. Till now, IGNOU reported soil texture is important in determining the nutrient holding, water movement and movement of soil air. Texture influences the permeability which generally decreases with decreasing particle size. Soil texture is important in determining the nutrient holding, water movement and movement of soil air. Texture influences the permeability which generally decreases with decreasing particle size. Soil texture is important in determining the nutrient holding, water movement and movement of soil air. Texture influences the permeability which generally decreases with decreasing particle size. Table 2.1. Table 2.1. Particle size of different soil components. Particle name. Size range. Sand 2 mm to 0.05 mm. Silt 0.05 mm to 0.002 mm. Clay less than 0.002 mm. Fig. 2.3 Soil texture triangle. Look at the screen. Soils have been categorized as fine, coarse depending upon its composition and size of the particles and Table 2.2. Look at the screen. Soil particles get grouped to form aggregates with pore spaces in between. Soils have also been divided into different grades and classes. Class it describes the average size of individual aggregates. Classes are of different types such as very fine, thin, medium, coarse, thick, and very coarse. Very thick. Grade it represents the degree of aggregation. It is based on the properties of cohesion and adhesion between soil particles or aggregates. The soils have been graded in the range of 0 to 3. 1. No aggregation i.e. no definite orderly arrangement of particles, structure. Less. 2. Poor aggregation between particles. Soil is referred as disturbed. Aggregates are broken. 3. 4. Well-formed distinct aggregates. A mixture of full aggregates, broken aggregates and some non-aggregated material. Strong durable aggregates. Very large aggregates and little no non-aggregated material. Different types of structural forms have been noted in soils, Table 3. These include plate-like, prismatic, columnar, block-like, spherical and granular. Variations in size are based on soil aggregates, paired. Paired is considered as the unit of soil structure. Soils have beds of different shapes. A well-developed granular structure facilitates aeration and water movement. Water movement and drainage are poor in soils having blocky, prismatic, columnar and platy structures. Plate-like, polty, they occur in any part of soil profile or are inherited from soil material. Prism-like, prismatic, columnar, they occur in subsoil particularly in arid and semi-arid region. Block-like, blocky, cube-like, subangular, present in subsoil particularly in humid regions. Spheroidal, granular, crumb, characteristic of soils subject to change. Table 2.3 Structure of Soil Particles. Look at the screen. 2.2.4 Soil Profile. A soil profile is a physical and chemical description of the layers, horizons, that make up the soil, from the surface to the depth, Fig 2.4. The layers of the soil are formed and are well differentiated from the original parent material. Horizons are labeled according to characteristic properties. Different layers of soil are formed with time, climatic changes, activities of living organisms, and relief. The system was developed by the U.S. Department of Agriculture, USDA. These layers are referred to as O, A, E, B, C and are depending on their position and nature. A typical profile of a mature soil includes the following horizons. Table 2.4 Description of different layers in soil horizon. O. Organic. Top layer dominated by organic material. It includes layer of litter and humus. This horizon is not present in cultivated soils, manicured lawns, and severely eroded soils. A. The mineral soil horizon present at the surface or below NO horizon is referred as topsoil. It contains a mixture of organic and mineral components. It has more organic carbon. This layer supports plants and microbial growth. This layer is formed when organic matter gets transformed into humic materials by soil biota. The humic materials coat the soil particles, coloring them brown and black. The formation of this horizon takes long time as decades. This horizon increases in thickness and soil content. E. Alluvial horizon characterized by alluviation, i.e., removal of materials such as silicate clay, iron, aluminum, or organic matter. It is commonly not found. Usually pale colored and low in organic matter. The texture is similar to horizon A. B horizon is dominated by loss of most of the original rock material and shows alluviation, i.e., concentration of the silicate clay, iron, aluminum, or humus from higher horizons. These materials get added by leaching from overlying horizons. This zone is formed when dissolved and suspended materials are carried downward to greater depths with percolating rainwater. It has various sub-horizons, which are denoted as BT1, BT2, BTG. C. It is the layer of soil excluding hard bedrock. It lacks characteristics of O, A, E or B horizons. Are the underlying hard bedrock. 2.2.5 Properties of soil. Properties of soil, whether physical or chemical, influence nutrient and water retention required for sustaining fertility and maintaining productive potential required for development of plants. Physical properties. Light and heavy soils. The presence of of high silt, particularly clay, gives it a fine texture but shows slow water and air movement. These soils become hard because of high water holding capacity. Such soils are called heavy soils. Are called light soils because they cannot retain water for longer period. Ecology and ecological factors. What makes up the organic matter component of soil? Name some factors affecting soil structure. Fig. 2.4 Various horizons in the soil profile. Properties of soil. Properties of soil, whether physical or chemical, influence nutrient and water Retention required for sustaining fertility and maintaining productive potential. Required for development of plants. Physical properties. Light and heavy soils. The presence of sand, silt or clay imparts a particular texture to soil. Presence of high silt, particularly clay, gives it a fine texture but shows slow water and air movement. These soils become hard because of high water holding capacity. Such soils are called heavy soils. In contrast, coarse, sandy and gravel soils. Soil pores. Pores are the spaces between soil particles or aggregates. They are important because they allow air and water to move through the soil. They are of different types. I. 2. Interstitial, small spaces between soil particles or aggregates. Tubular, bigger tube-like spaces made by plant roots or soil animals. Pores are generally broken up into two size classes depending upon the size. I. 2. Macropores, bigger pores that allow free movement of air and water. Micropores, small pores that help in movement of air and water by capillary action. Soil color. Color is the most useful property for identification of soil, Table 2.5. It is determined by the amount of organic matter and iron. Colors of soil matrix and mottles indicate water and drainage conditions in the soil. These colors may occur as the dominant color, the matrix, or in patches, mottles. The color of the soil can be quickly determined by comparison of the sample with a standard set of color chips mounted in a notebook called Munsell color chart, figure 2.5. Soil color is described by the parameters called hue, value, and chroma. Hue describes, wherein delete, the color spectrum where the color of soil exists, colors yellow, red, blue, green, and gray. Chroma indicates the strength of the color. Table 2.5, Soil color and their respective properties. Soil color. Properties. Rich brown color, well-aerated soils with pore space dominated by oxygen. Gray or blue-gray colors, poorly drained soils, wet soils developed under anaerobic conditions. Brownish black or dark brown colors, high organic content like Horizon A soil. Red and yellow soil, presence of iron oxides and indicates good drainage and aeration. Yellow color, presence of hydrated iron oxides and hydroxide. Black indicates manganese oxides. Temperature. Temperature. Soil temperature influences its properties. Fluctuations in temperature help the physical breaking of rock and mineral grains. Lower temperature affects accumulation of organic matter because of low biological activity. Increase in soil temperature influences its properties. Fluctuations in temperature help the physical breaking of rock and mineral grains. Lower temperature affects accumulation of organic matter because of low biological activity. Increase in soil temperature influences its properties. Fluctuations in temperature help the physical breaking of rock and mineral grains. Lower temperature affects accumulation of organic matter because of low biological activity. Increase in temperature. Drainage. Support chemical weathering. Soil drainage indicates status of soil when it is saturated, water in excess of field capacity. Excess free water in the root zone can kill plants or pose. Agriculture recognizes 7 classes of drainage ranging from excessively drained, where the water Moves out of the soil rapidly to very poorly drained, where water moves out of the soil very slowly. Drainage is affected by soil texture. The coarser so. Soil drainage indicates status of soil when it is saturated, water in excess of field capacity. Excess free water in the root zone can kill plants or pose difficulty in their establishment. The U.S. Department of Agriculture recognizes 7 classes of drainage ranging from excessively drained, where the water moves out of the soil rapidly, to very poorly drained, where water moves out of the soil very slowly. Drainage is affected by soil texture. The coarser so tend to drain more rapidly. The shallow soils tend to drain more rapidly. This property also depends upon rate of precipitation. The areas with greater rainfall may drain slowly. Topography also influences drainage as ground level soils drain slowly. Soil drainage indicates status of soil when it is saturated, water in excess of field capacity. Excess free water in the root zone can kill plants or pose difficulty in their establishment. The U.S. Department of A. 7 classes of drainage ranging from excessively drained, where the water moves out of the soil rapidly, to very poorly drained, where water moves out of the soil very slowly. Drainage is affected by soil texture. The coarser so tend to drain more rapidly. The shallow soils tend to drain more rapidly. This property also depends upon rate of precipitation. The areas with greater rainfall may drain slowly. Topography also influences drainage as ground level soils drain slowly. Hills tend to drain more rapidly. The shallow soils tend to drain more rapidly. This property also depends upon rate of precipitation. The areas with greater rainfall may drain slowly. Topography also influences drainage as ground level soil consistence. Soil consistence. Soil particle form aggregates. Soil particle form aggregates. The aggregates arrange into discrete structural units called beds. Between the beds are present pores. The aggregates arrange into discrete structural, which play an units called beds. Between the beds are present pores. Important role in movement of air and water, which play an soil consistence is the property of breaking down of beds. It depends on the soil moisture content. The resistance of a soil to deformation or rupture is determined by the cohesive, coarse textured soils poses lar of breaking down of beds. It depends on the soil moisture content. The resistance of a soil to deformation or rupture is determined by the cohesive and adhesive properties of the soil. Large GE play important role in movement of air and water. Soil consistence is the property of breaking down of beds. It depends on the soil moisture content. The resistance of a soil to deformation or rupture is determined by the cohesive and adhesive properties of the soil. Coarse textured soils poses lar spaces that lead to high infiltration, percolation and drainage, while fine textured soil contains small pores and high amount of surface water. Spaces that lead to high infiltration, percolation and drainage, while fine textured soil contains small pores and high amount of surface water. Spaces that lead to high infiltration, percolation and drainage, while fine Textured soil contains small pores and high amount of surface water. Bulk density. Bulk density is the weight of a given volume of overnight soil divided by the volume, i.e., mass of soil per unit volume of soil. It is expressed as weight per volume and generally represented as grams per cubic centimeters, GCC. The formula for its calculation is dB is equal to MSVT, where dB is equal to bulk density, MS is equal to mass of solids, VT is equal to total volume. Soil bulk density values range from 0.5 to 3.0, but most values are between 0.8 and 1.8. It reflects the amount of pore space in the soil and is an indicator of soil health. It is inversely proportional to pore space. Pore space is equal to 1 bulk density particle density. For example, at a bulk density of 1.60 GCC, pore space equals 0.40 or 40%. At a bulk density of 1.06 GCC, pore space equals 0.60 or 60%. Soil texture, organic content and compaction affect the property of bulk density. High bulk density indicates compacted soils. The plant growth is restricted in these soils. The practices such as cover cropping, addition of crop residues increase organic matter, thereby reducing bulk density. Example A. Soil with 100% mineral soil material and bulk density of 1.33 GCC, while another soil with 95% mineral soil material and 5% organic soil material has bulk density of 1.26 GCC. The difference in bulk density relates to a difference in mineral soil material and organic soil material. The average particle density of mineral soil material is 2.65 GCC, while that of organic soil material is 1.25 GCC. Lower the pore space or higher the bulk density of the soil, the higher the suitability of the soil for aquaculture. Soil permeability. The rate at which water moves down through the soil is referred as permeability. It is usually measured in inches per hour. Pore size, texture, structure, organic content, and compaction determine the permeability of a soil. Rate or coefficient of permeability is determined by measuring rate of flow of water through a column of soil. The permeability differs for various layers of soil horizon. The property depends upon the pores between soil particles. Soils with high clay content poses low permeability, while sandy soils have a higher permeability. A sandy loam has a permeability of 2.0 to 6.0 inches per hour, while sandy clay loam has a permeability of 0.2 to 0.6 inches per hour. In an impermeable soil, water is lost through seepage and infiltration is low. Infiltration is the rate at which water enters the soil. Applying water at rates greater than what soil can take results in ponding. The increase in runoff leads to soil erosion and loss of fertility. Organic matter improves soil structure, improving permeability and infiltration. Fine textured soils, clayey, contain more total pore space than coarse textured soils, sandy. Water moves more slowly through a fine textured soil, leading to lower permeability and infiltration. Calcium improves soil structure by encouraging aggregation and increasing pore size. This increases permeability and infiltration. Microorganisms, e.g., bacteria and fungi, and macroorganisms, e.g., insects and earthworms present in the soil increase permeability and infiltration by encouraging the formation of soil aggregates and creating macropores in the soil. Infiltration is influenced by factors such as dryness and slope. Dry soils repel water. This is true for soils rich in organic content. Slope may cause water to run off. Odor. Odor is the indicator of wetness. In waterlogged soils, bacteria use oxygen for respiration, releasing hydrogen sulfide gas that smells like rotten eggs. Sulfur. Smell is prevalent in soils around marshes or overwatered potted plants. Water holding capacity. The amount of water the soil can hold against the flow of gravity is also called as field capacity. The maximum amount of water that the soil can hold is called water holding capacity. It is the difference between the amount of water in the soil at field capacity and the amount of water in the soil at wilting point. It is also referred to as available water capacity, AWC, or plant available water. PAW. It is measured in inches foot or inches inch. The soil moisture content. After soil cannot support agronomic plant growth is referred as wilting point. Soil texture plays an important role in this property. Sandy soils possess low water holding capacity, while clayey soils tend to have a higher water holding capacity. Very high clay content reduces water holding capacity because the tiny pores between the particles hold water tightly. Chemical properties. Cation exchange capacity, CEC. Soil can hold some amount of cations which are present in an exchangeable form. The total number of charged sites present on soil particles within a given volume of soil is known as ion exchange capacity. Total number of negatively charged sites present on the clay particles and humus is called cation exchange capacity, CEC. It depends upon the number of exchange sites on clay particles and net charge of soil particles or magnitude of the negative charge per unit weight of soil. This property increases in soils with high clay and organic matter content. Clay and organic matter particles are negatively charged anions. They attract cations, positively charged particles, to their surfaces. The bonds between the clay mineral surface and the cations are relatively weak, hence cations get exchanged for other cations dissolved in the solution. When the adsorbed cations get replaced by other cations, the process is called cation exchange. The greater the clay and organic matter content, the greater the CEC. It is determined in terms of milliequivalents. ME per milligrams of soil. If soil has a CEC value of 1 meter E, this means that it is capable of holding milligram of hydrogen or equivalent for every 100 g of soil. Elements like calcium have two charges equivalent to 2 hydrogen ions. The amount of calcium required to displace 1 milligram of hydrogen is 40 Houses i.e. 20 milligrams. CEC depends upon the quantity of exchangeable hydrogen ions and other bases present in the soil. Cation exchange is an important property of soils for retaining nutrients and increasing their availability to plants. Cations present in soils mainly include nutrients such as potassium, calcium, and magnesium. The loosely held nutrients can then be taken up by plant roots or by other soil organisms. This property helps soil to filter environmental contaminants from wastewater. Soil pH. The acidic or basic nature of the soil depends upon the relative concentration of H ions, acidity, or O ions present in it. Acidity is due to the presence of excess of H ions, while alkalinity is due to the excess of O ions. The pH scale ranges from 0 to 14. Values below 7.0 are acidic and above 7.0 are alkaline. A pH value of 7 is considered neutral, where H plus and O are equal, both at a concentration of 107 moles liter. Indication of the acidity or alkalinity of the soil is also known as soil reaction. pH of soil affects solubility of ion, which in turn affects microbial and plant growth. A pH range of 6.0 to 6.8 is ideal for most crops because it provides optimum solubility of the most important plant nutrients. In acid soils, hydrogen and aluminum are the dominant exchangeable cations. Factors that affect soil pH include parent material, vegetation, and climate. Types of soil. The soils have been differentiated into different types depending upon the basis of their origin and relationship with the parent rock. Residual soils. These soils are formed at the same site where the weathering of the parent material takes place, i.e., formed under in situ conditions from underlying rocks. In India, these soils are of two types: reddish soils, which are poor in calcium, magnesium, phosphorus, and nitrogen but rich in iron oxides, and black soil, which is rich in clay and possesses high quantities of potash, calcium, magnesium, and iron. Transported soils. These soils are formed from weathered material which is transported and deposited away from the site of origin. These soils are of different types depending upon the type of agent involved in its transport. Times colluvial. These soils are formed from material transported by pull of gravity or under conditions of landslide. It is very coarse and consists of large fragments of rock. Alluvial. The soil is formed under conditions of running water such as flood plains, river terraces, and delta. The soil particles are rounded and smooth. The particle size varies depending upon the speed of transporting water. Times glacial. These soils are formed by the grinding action of ice and snow. Heavy snow masses and glaciers push the surface material. Sharp-edged rocks get grounded into smooth particles by abrasive action. Times aeolian. The soils formed by transportation through wind. These include dunes and loess. They occur along the side of water bodies. The water currents erode the land and lead to deposition of soil particles. Classification of soils. Soil scientists have come up with systems for classifying soils. Soil taxonomy. Experts from Russia, FAO, and Canada have classified the soils on the basis of genesis, i.e., development. Soils have been classified into 12 categories or orders. Table 2.6. Table 2.6. Classification of soils. Look at the screen. In India, 6 types of soils are found. These include alluvial soil. Soil which is deposited near rivers, seas, and glaciers is called as alluvial soil. It is found in Indo-Ganga-Brahmaputra plains, coastal plains, and the broad river valleys of South India. Red soil. Soil that develops under very low rainfall condition on granite and rocks is referred as red soil. The presence of oxides of iron gives them red color. Found mainly in almost whole of Tamil Nadu, southeastern Karnataka, northeastern and southeastern Madhya Pradesh, Jharkhand, the major parts of Odisha, and the hills and plateaus of northeast India. Black soil, it is very clayey thick in texture. It possesses high water holding capacity and is very fertile. This type of soil is best for cultivation of cotton. Found in plateaus of Maharashtra, Gujarat, Madhya Pradesh, mainly Malwa. Mountain soil, it is formed by deposition of organic matter provided by forests. It is rich in humus and heterogeneous in nature. It is sandy and porous. Found on the hill slopes covered with forests, particularly the Himalayan region. Laterite soil, it is a kind of clayey soil formed under high temperature and high rainfall. Found mainly in South Maharashtra, the western Ghats in Kerala and Karnataka, at places on the eastern Ghats, in some parts of Assam, Tamil Nadu, Karnataka. Desert soil, the soil has sand 90 to 95% and clay 5 to 10%. In some regions, this soil has the high percentage of soluble salts but lacks in organic matter. Found mostly in the arid and semi-arid regions, receiving less than 50 centimeters of annual rainfall. 2.2.6 Soil biota and fertility. Soil biota, i.e., living organisms present in soil, play an important role in soil formation and development. Table 2.7. Soil organisms alter soil physical, chemical and biological properties of the soil in different ways. The biotic communities influence the spatial heterogeneity of resource. Biological functions of soil biota help in improving soil health, function, quality, fertility, and provide a sustainable alternate for soil management. Soil formation and improvement of soil structure is the major function performed by soil biota. Bacteria present abundantly in soil secrete mucilaginous and organic substances which cover cells and their colonies. These substances help in cementing the soil grains to form larger aggregates. Fungi present in the soil also help in binding the soil particles together. Larger soil organisms such as rodents, insects and worms help in mechanical mixing and weathering of soil. The roots of plants widen the fissures in rocks, helping in their breakdown to form small fine particles. Invertebrates play a role in stabilizing soil structure. Earthworms help in mixing of soil but make it more fertile by increasing aeration and drainage. They bring down the lower soil to the surface and mix soil by digging burrows. Burrowing activities bring subsoil to the surface. It also helps in the creating passage for gaseous exchange, i.e., diffusion of oxygen and release of carbon dioxide. Decay and nutrient cycling is another major function performed by organisms present in the soil. These organisms act as chief agents of decay in organic matter. Decomposition and mineralization help in the release of inorganic nutrients that are absorbed by the plant roots. Organisms include bacteria, actinomycetes and fungi. These organisms bring out hydrolysis and oxidation of organic compounds through various enzymatic reactions. Soil fauna such as millipedes, centipedes, earthworms, mites, ants, beetles and snails consume plant products, litter, and leave the decomposed product in soil. The complex organic compounds are broken down into simpler compounds. Example proteins are broken down into amino acids, ammonium compounds, nitrates and nitrites. Worms utilize undecomposed remains of plants and animals as food. In the process, they convert it into useful organic matter. Nitrogen fixation is another important function performed by microbes present In the soil, microorganisms such as Azotobacter, Clostridium, Rhizobium help in fixation of atmospheric nitrogen by converting the atmospheric nitrogen to organic nitrogen. The fixed nitrogen is utilized by other organisms. The amount of nitrogen fixation has a direct effect on soil fertility. Heterotrophic soil organisms including bacteria and fungi produce growth, promoting substances such as 3-indole acetic acid and other delete. These substances support the growth of plants. Table 2.7 Common populations of some soil microorganisms. Organism count, number, G of soil. Bacteria 108,109. Actinomycetes 107,108. Fungi 105,106. Algae 104,105. Protozoa Nematoda 104,105. 10,102. In the table, the numerals indication the power to which the figure 10 is multiplied is not clearly seen. Please correct this table for easy reading. 2.3 Water. Water is a tasteless, odorless and colorless liquid with the chemical formula H2O. Henry Cavendish, 1781, showed that water is composed of oxygen and water is a tasteless, odorless and colorless liquid with the chemical formula 1781 showed that water is composed of oxygen and hydrogen. Joseph Louis Gay-Lussac, Humboldt, and Alexander Vaughan showed that water is composed of 2 parts hydrogen and the first sample of pure 1805 showed that water is composed of 2 parts hydrogen and 1 part oxygen. The first sample of pure Newton Lewis. Heavy water. In 1933. In a water molecule, 2. In a water molecule, 2. Was isolated by Gilbert. Hydrogen. Covalently bonded to a single oxygen. Atoms. Atom. The oxygen atom is atom. The oxygen atom is lone pi rupees r of electrons. The angle between the hydrogen atom and oxygen is 109.47 degrees, Fig 2.6. The lone pairs of delete are located in the direction electronegative and possesses to lone pi. The hydrogen atom and oxygen is 109.47 degrees, Fig 2.6. The lone pairs of electrons on the oxygen atom and delete are located in the direction opposite to that of hydrogen atoms. 2.3.1 States of water in the environment. Water occurs in 3 phases: solid, liquid, gas. The liquid is the most common phase. It remains as a liquid because of oxygen, which is electronegative in nature. The solid phase, the gaseous phase of water, is known as ice. Of water is known as water vapor. State is supercritical fluid. Steam, the fourth, and is not very common. At a specific critical temperature and pressure 647 K and 22.064 MPa, the liquid and gas phases merge to one homogeneous fluid phase. Supercritical water is the hot water occurring naturally in deep hydrothermal vents. 2.3.2 Types of precipitation. Interchange of water occurs: delete, between Earth's surface and atmosphere occurs via precipitation. It is the form of water which comes down on Earth from the sky or atmosphere. It forms an important part of hydrologic cycle. It is essential for sustaining life on Earth. Precipitation plays a key role in renewing our natural water resources. Precipitation is of different types. Fig. 2.7. Rain. In this type of precipitation, water falls down in the form of drops from the clouds in the sky. The water droplets are 0.5 millimeters or larger. Rain is important component of water cycle and replenishes major portion of fresh water on Earth. When the droplets are smaller in size, i.e., less than half a millimeter, it is referred as drizzle. The rate of rainfall varies across various regions of globe. Rainfall has been categorized into three types. Light, when water drops fall at the rate of 0.01 to 0.1 inches per hour. Moderate, when water drops fall at the rate of 0.1 to 0.3 inches per hour. Heavy, water drops fall at the rate of more than 0.3 inches per hour. Snow. In this type of precipitation, solid form of water, i.e., snowflakes fall down on Earth. Snow is formed when the atmospheric temperatures are above freezing. Snow has fluffy, white and soft structure. It is of different shapes such as flat plates and thin needles. The type of snow formation depends upon the humidity and temperature conditions. The process of snow precipitation is called snowfall. Hail. It is a form of precipitation in which big balls and irregular lumps of ice, hailstones, fall on Earth as a result of thunderstorms. It is a kind of solid precipitation. Hailstones are formed from supercooled droplets of water and measure from 0.2 inches, 5 millimeters, to 6 inches, 15 centimeters, in diameter. Hailstones are noted in winter or cold weather. Dew. It is a type of precipitation in which water droplets are formed on the objects near the ground through condensation of moisture. During clear nights, the exposed surfaces are cooled by radiation, heat. Exposed surfaces are cooled by radiation, heat. Moisture condenses, resulting in the formation of water droplets. Delete, and the atmospheric moisture condenses, resulting in the formation of water droplets. Sleet, ice pellets. It is a type of precipitation composed of small and semi-transparent balls of ice. The formation of sleet takes place in freezing atmospheric conditions. Snow falls, comes in contact with warm air, melts into rain. Rain droplets fall into a freezing layer of air and convert raindrops into ice pellets. This form of precipitation is experienced during thunderstorms. 2.3.3 Global distribution of water. Water is distributed across various regions of Earth. Oceans cover roughly 70% of the area of the Earth. They reflect blue light, and hence the Earth appears blue from space. Therefore, Earth is also referred as. Water is distributed across various regions of Earth. Oceans cover roughly 70% of the area of the Earth. They reflect blue light, and hence the Earth appears blue from space. Therefore, Earth is also referred as. Total volume of water on Earth is estimated at 1.386 billion kilometers superscript 3, 333 million cubic miles. Out of the total water available, only 3% of water is freshwater, and remaining 97% is saline, Fig 2.8. Most, 97% of the water P. Blue planet. The total volume of water on Earth is estimated at 1.386 billion kilometers superscript 3, 333 million cubic miles. Out of the total water available, only 3% of water is freshwater, and remaining 97% is saline, Fig 2.8. Most, 97% of the water P. Earth is saline. Average salinity is 35% or 3.5%. This is equivalent to 34. Recent on is 35% or 3.5%. This is equivalent to 34 kg of seawater or grams of salts dissolved in 1 kilogram of seawater or dissolved per liter of seawater. Water with a salinity level between 0.35% and 1 per thousand is referred as marginal water. The ratio of salt water to fresh water on Earth is around 40 to 1. 35,000 milligrams of salt ions. Water with a salinity level between 0.35% and the ratio of salt water to fresh water on. Of the total freshwater, about 69% exists in the form of ice, snow, 30% as. Of the total freshwater, about 69% exists in the form of ice, snow, 30% as. About 0.3% as liquid. This means that only 1% of the water is available for use by humans and rest, 99%, is underground. Of the total liquid surface fresh water, 87% is contained in lakes, 11% in swamps, and 2% in rivers. Approximately 680,000 groundwater and less than 1%, about 0.3%, as liquid. This means that only 1% of the water is available for use by humans and rest, 99%, is underground. Of the total liquid surface fresh water, 87% is contained in lakes, 11% in swamps, and 2% in rivers. Approximately 680,000 present in the form of glaciers and permanent snow ice cover. These include water resource present as ice sheets in the Antarctic, Arctic and Greenland. This water is not accessible. Melting glaciers provide a natural source of river water and groundwater. Kilometer 2 of freshwater is glaciers and permanent snow ice cover. These include water resource present as ice sheets in the Antarctic, Arctic and Greenland. This water is not accessible. Melting glaciers provide a natural source of river. Fresh water is defined as water with a salinity. Fresh water is defined as water with a salinity less than 1% that of the is called as freshwater. Oceans i.e. below around 0.35% is called as freshwater. Lakes provide an excellent source of freshwater for human use. Include the lakes as well as ponds, reservoirs, rivers and streams and wetlands. The flow of water into these water bodies comes from rainfall, runoff, delete. Rivers and melting snow, ice and base flow from groundwater systems. Surface waters account for small volume, 0.3% of the Earth's total freshwater resources. Lakes store the largest volume of fresh surface waters, 90,000 kilometer 3. This accounts for 40 times more water than the water found in rivers or streams. Lakes, they delete, are estimated to cover a total area of about 2.7 million kilometer 2. This represents around 2% of the land's surface, excluding polar regions. Mostly lakes are small, but world's 145 largest lakes are estimated to contain over 95% of all lake freshwater. Lake Baikal, Russia, is the world's largest, deepest lake, which contains 27% of the freshwater contained in lakes. Lake waters provide many services such as fishing, recreation, transport, and water supply for the world's population. The total volume of water stored in rivers and streams is estimated at about 2,120 cubic kilometers. A large area of subsurface, porous rock that holds water is an aquifer. Aquifers are commonly drilled and have wells installed in them to provide water for agriculture and personal use. Wetlands are water-saturated environments and are commonly characterized as swamps, bogs, marshes, mires and lagoons. Wetlands cover an area about 4 times greater than the world's lakes. They contain only 10% of the water found in lakes and other surface waters. They cover total of about 6% of the Earth's land surface. Water is used mainly for irrigation, 68%, public supply, 21%, and industry, 11%. Water existing in the voids of the geological stratum below the surface of the Earth is called groundwater. It is found enclosed in pores and fissures of rocks. Out of the total 13,84,12,000 cubic kilometer of water existing on Earth, about 800,042 cubic kilometer is groundwater. Groundwater comprises 95% surface water, 3.5%, and soil moisture, 1.5%. Out of all the fresh water on the Earth, only 0.36% is readily available to use. Around 61,234 cubic kilometer of water exists in the form of soil moisture. Groundwater and soil moisture together constitute the subsurface water. Groundwater is 0.58% of the total water resources available in nature. It is located up to a depth of 4 kilometers below the Earth's surface. Most of the groundwater originates as meteoric water from precipitation in the form of rain or snow. Rain or snow melt infiltrates the ground and moves downward to form groundwater. Groundwater is stored in different layers of earth by infiltration through pores and fissures of permeable rocks. It is present in small spaces, pore space, between mineral grains and subsurface of rock or sediments. The main source of groundwater is rainfall. It infiltrates through seepage slowly into the earth and collects there. It is also called plutonic water. Other sources of groundwater include seepage from surface water, lakes, rivers, reservoirs, and swamps, irrigation, and underground wastewater treatment systems, septic tanks. Morris et al. 2003 reported that groundwater systems provide 25 to 40% of the world's drinking water. Groundwater is an important part of the water cycle because surface and atmospheric water goes underground through rainfall, rivers, and lakes. Groundwater mainly comes from 3 sources. I. Meteoric water. This is the main source of groundwater. This water is received in the form of rain and snow, hence it is called meteoric or shooting star water. Water infiltrates down through rock joints, pores, fissures of rocks and is stored in the form of groundwater. Groundwater can directly be derived from atmospheric moisture via condensation of water vapor from circulating air present in pore Spaces. This is also known as condensational water. It is the basic source of water in arid and semi-arid areas. The difference in the temperature between land and air during summers cause a difference of pressure between the water vapor in the atmosphere and the soil. This results in penetration of water vapor into soil, seepage of water from lakes, rivers, oceans and also man-made channels adds to groundwater. This occurs mainly in the humid regions. 2. Connate water. Water contained in pores and cavities of sedimentary rocks under seas and lakes is called connate water. It is also called sediment water. It is the second important source of groundwater. This water is entrapped in the interstices of sedimentary and volcanic rocks at the time of deposition. This water is highly mineralized and salty. 3. Magmatic water. Water that gets converted to vapors after condensation of delete as a result of volcanic action at the time of entering hot rocks is called magmatic water. Hot magma enters rocks due to volcanic action, after which its vapor drops are condensed and converted into water. This is called magmatic water. Springs, wells, and geysers are sources of such water. It is generated in the interior of the earth but consequently travels to the upper layers of the earth's surface. 2.3.4 Properties of water. A molecule of water consists of two atoms of hydrogen, H, joined to one oxygen, O, atom via covalent bonds. The two atoms i.e. H and O are bound to each other asymmetrically with two H atoms at the end and atom of O in the center. Water is a polar solvent. A single molecule of water possesses two lone pairs of electrons on oxygen atom and two hydrogen atoms. Oxygen attracts electrons much more strongly than hydrogen, resulting in a net positive charge on the hydrogen atoms and a net negative charge on the oxygen atom. The difference in electronegativity leads to dipole moment, making the oxygen partially negative and each hydrogen partially positive. These atomic charges give water molecule a net dipole moment, Fig 2.9. Electrical attraction between water molecules due to dipole moment pulls the water molecules closer together, making it difficult to separate, thereby raising the boiling point. The charge differences make the water molecules to attract each other, the relatively positive areas being attracted to the relatively negative areas and other polar molecules. This attraction contributes to hydrogen bonding. Look at the screen. Water dissociates or ionizes into a hydronium ion and hydroxide ion. Hydrogen bonding is responsible for many physical properties of water. Water is a solvent that dissolves many substances in comparison to any other liquid. It acts as a fluid that dissolves and transports molecules of nutrients and metabolites, helps in regulation of temperature and maintenance of the chemical equilibrium within the living cells. Physical properties of water. 1. High boiling and melting point. It possesses a high melting and boiling point. Strong bonding between oxygen and hydrogen atom occurs due to electronegativity of oxygen, and hence more energy is required to break the hydrogen bonds between water molecules. 2. Specific heat. Water molecules are linked to each other by hydrogen bonds. The bonding between water molecules, water delete, leads to high specific heat. If water is to be heated, more energy is required to break hydrogen Bonds between molecules. About 4.18 joules of energy is required to heat 1 gram of water by 1 OC. The energy used for heating water by 1 OC is called specific heat. Hence, the specific heat of water is 4.1814 joules. Joule. 3. Miscibility. Water acts as a good solvent because of high polarity. Salts or substances mix well and dissolve in water. The substances that dissolve in water are called as hydrophilic water-loving substances, while those that do not mix well with water are known as hydrophobic water-fearing substances. Water is miscible with many liquids. It is capable of forming a single homogeneous layer of liquid. Water, being a relatively polar compound, tends to be miscible with ethanol and acetone. When an ionic or polar compound enters water, it is surrounded by water molecules. Hydration. The partially negative dipole ends of the water are attracted to positively charged components of the solute. Ionic and polar substances such as acids, alcohols, and salts are relatively soluble in water. Non-polar substances such as fats and oils do not dissolve in water. Non-polar molecules stay together in water because water molecules hydrogen bond to each other and form van der Waals interactions with non-polar molecules. 4. Enthalpy, latent heat. It is the amount of energy, is the delete, required to melt ice from 160 degrees C up to its melting point, or to heat the same amount of water by about 80 degrees Celsius. The specific enthalpy of fusion of water is 333.55 kJ/kg at 0 degrees Celsius. 5. Density. The density of water is about 1 gram per cubic centimeter. The density varies with temperature. The density rises with increase in temperature, followed by a decrease. Water molecules come close to each other at low temperature and hence density increases. Water is most dense at 4 degrees Celsius. At low temperatures, movement of water molecules ceases. The bonds between molecules become relatively fragile. Air molecules get trapped between moieties of water. This makes the ice lighter than water. 6. Vapor pressure. The vapor pressure is the pressure at which water vapor, gaseous form of water, is in thermodynamic equilibrium with its condensed state. The temperature and pressure at which solid, liquid, and gaseous form of water coexist in equilibrium is called the triple point of water. This point is given in units of temperature, i.e., Kelvin, degrees Celsius, and Fahrenheit. 7. Electrical conductivity. In pure form, water cannot conduct electricity and acts as an insulator. If water has a salt or solute dissolved in it, then it can conduct electricity. 8. Cohesion and adhesion. Water molecules stay close to each other because of hydrogen bonds between water molecules. This property is called cohesion. Water also has high adhesion properties because of its polar nature. Water forms a thin film on extremely clean smooth surfaces such as glass. This is because of stronger molecular forces between glass and water molecules, adhesive forces. The property of cohesion is responsible for the viscosity of water. It is the property of a material that measures the force necessary to separate the molecules and allow the object to pass through the liquid. In biological cells and organelles, water is in contact with membrane and protein surfaces which are hydrophilic. 9. Surface tension. Water has a high surface tension in comparison to other liquids. The cohesive forces between water molecules lead to high surface tension. Surface tension tends to straighten the surface, causing a rise pull-up in water. 10. Capillary action. Water exhibits capillary action. This is a property where water rises into a narrow tube against the force of gravity. This occurs due to interplay of the forces of adhesion and surface tension. In this manner, water is carried through xylem, upstem of plants. The strong intermolecular attractions, cohesion, hold the water column together, and adhesive properties maintain the water attachment to the xylem and prevent rupture caused by transpiration pull. Chemical properties. 1. Geochemistry. Water leads to weathering of rocks. The physical and chemical processes convert solid rocks and minerals into soil and sediment. Water, ice, can form clathrate compounds, known as clathrate hydrates, with a variety of small molecules that can be embedded in its spacious crystal lattice. For example, in chemistry, water of crystallization or water of hydration are water molecules that are present inside crystals. 2. Acidity. Pure water has the concentration of hydroxide. The hydronium ions, O, equal to that of H3O+, or hydrogen, H+, ions, which gives pH of 7 at 298 K. Water possesses a capacity to absorb carbon dioxide from the atmosphere or water to form carbonic acid. This dissociates further to form hydrogen ion and bicarbonate ion. The dissociation of bicarbonate ion produces hydrogen ion. The abundance of hydrogen ions gives the measure of acidity. More is the number of hydrogen ions, more acidic is the solution. 3. Acid-base reactions. Water is amphoteric. It has the ability to act as either an acid. Chemical reactions. According to the Bronsted-Lowry, or a base. Definition: an acid is a proton, H+, in donor, and a base is a proton acceptor. When reacting with a stronger acid, water acts as a base. Similarly, when reacting with a stronger base, it acts as an acid. Oxygen present in the water molecule possesses two lone pairs of electrons, hence it acts as a Lewis base. Electron pair donor. It forms hydrogen bonds between the donors and hydrogen atoms of water. 4. Redox reactions. Water contains hydrogen which has an oxidation state of 1 and oxygen which has an oxidation state of 2. It oxidizes chemicals such as hydrides, alkali, metals, and some alkaline earth. Oxidize to emit oxygen gas. 5. Electrolysis. Metals. It can be. Water can be split into its constituent elements, hydrogen and oxygen, by passing an electric current through it. This process is called electrolysis. 2.3.5 Water cycle. The mechanism by which water moves from dilute through different components of environment, i.e., air, water and land, is called the water cycle. Solar energy and gravity drive the movement of water through different components of water cycle. The water present in the water body's reservoirs such as oceans, atmosphere, glaciers, groundwater, lakes, and rivers, gets heated up and escape into the atmosphere as vapor, gaseous form of water. This process is known as evaporation. Hence, evaporation is an important component of the hydrological cycle. Fig 2.10. Water also returns to atmosphere via transpiration, i.e., loss of water by plants. The changes in temperature condense vapors to form clouds. The water comes down on Earth as precipitation, which can be of different types such as rain, dew, snow, or hail. The rainfall pattern is mainly related to wind circulation. Global precipitation pattern is also affected by ocean currents, mountains, and continents. More precipitation falls near the equator, whereas less precipitation tends to fall near north and south latitudes. The processes of evaporation and transpiration. Evapotranspiration regulate the water found in soil, i.e., soil moisture content. The water on land can either return to the oceans or other water bodies by surface runoff, rivers, glaciers, and subsurface groundwater flow. The water present in river, lakes, and aquifers is referred as blue water. Water used by plants and subsequently released into the air is called as green water. 2.4 Summary. Soil is one of the important constituents of the environment. It is a complex system consisting of mineral matter derived from rocks, organic matter obtained from death and decay of plants and animals, air, and time. Soil is one of the important constituents of the environment. It is a complex system consisting of mineral matter derived from rocks, organic matter obtained from death and decay of plants and animals, air, and water. Time. Soil formation involves processes such as weathering and humification. Times. Based on sites of origin, soil has been classified as residual and transported. Residual soils develop at site where parent rock material is present. Transported soils develop when the parent rock material is carried to distant places, depending upon the agent involved in their transport. Soils are classified into different groups: colluvial, by gravity; glacial, by ice and snow; aeolian, by wind. Based on sites of origin, soil has been classified as residual and transported. Residual soils develop at site where parent rock material is present. Transported soils develop when the parent rock material is distant places, depending upon the agent involved in their transport. Soils are classified into different groups: colluvial, by gravity; glacial, by ice and snow; aeolian, by wind. Time. Soil is made up of particles of various sizes, shapes mixed in different proportions. Based on the size of soil particles, they have been classified into different types such as clay, silt, sand, coarse, and gravel. Soil is made up of particles of various sizes, shapes mixed in different proportions. Based on the size of soil particles, they have been classified into different types such as clay, silt, sand, coarse, and gravel. Times. The proportion of clay, silt, and sand particles decide the texture of the soil. The soil structure comprises of S. The proportion of clay, silt, and sand particles decide the texture of the soil. The soil structure comprises of S. Oil particles arranged in aggregates. Soil with high proportion of sand and gravel is called as light Soil while that having high proportion of clay and silt is referred as heavy. Aggregates. Soil with high proportion of sand and gravel is called as light. Soil while that having high proportion of clay and silt is referred as heavy. Soil. Permeability and aeration are important soil properties that influence the availability of water and gases. Poor aerated soils affect root growth because of limited availability of nutrients and water. Times cation exchange capacity, CEC, is an important soil property that helps in making the nutrients such as Ca, Mg, K, Na, Cu, Mn, Zn available to plants and organisms present in the soil. It is the total number of exchange sites on the soil colloids including humus and clay particles. Times fauna and microorganisms present in the soil play a major role in making it fertile. Decomposition processes, production of growth substances, secretion of organic acids help in binding soil particles. Formation of aggregates, aeration and buildup of organic matter. They also help in nutrient cycling via nitrogen fixation. Times water, as a solvent, is critically essential for the existence of living beings. Times it is a universal solvent that facilitates chemical reactions within the living organisms. Times water is classified into two types, namely fresh water and saline. Marine water depending upon salt content present in it. Each form of water contains varying amounts of dissolved salt, K, Na, Mg, content. Times high dipole moment and strong hydrogen bonding in water molecule contributes to properties such as high boiling point, miscibility, specific heat, surface tension. Times water is distributed in various components of environment via water cycle. Cycling of water depends upon the processes such as evaporation, condensation, and precipitation. Thank you for watching. We will see you in the next video with the next chapter.